Hello everyone and welcome to the MATLAB based demonstration on signal scaling. In digital signal processing, signal scaling is an important basic operation which is used to change the amplitude of the signal without changing its fundamental shape or time characteristics. In this video, we will understand the concept of signal scaling and see how it can be implemented easily using MATLAB. We'll take a given input signal, multiply it by a suitable scaling factor, and observe the resulting output. And finally, we will plot and compare the original and scaled signals to clearly visualize the effect of amplitude increase or decrease. So let's begin. Now first we'll see what is signal scaling. Signal scaling, it is the process of multiplying a signal by a constant value called the scaling factor, which is represented by alpha. And it changes the amplitude, that is the strength of the signal, without changing its frequency, shape or phase. So in signal scaling, only the amplitude is changed. There is no change in frequency, shape or phase. Mathematically, we'll represent it as y of n is equal to a, or you can take it as alpha into x of n. So original signal is what? X of n. This alpha, it is the scaling factor which will be a constant, and y of n is the scaled signal, that is the output. Now here these are the effect of the scaling factor. What happens when the scaling factor is greater than 0, when it is equal to 1, or when it is less than 0. Now, when the scaling factor is greater than 1, amplitude increases. That is, the signal is amplified. So, this is x of n. If a is greater than 1, then your amplitude increases. You can see the difference between the amplitude of x of n and y of n. Next, if a is in between, that is, it is less than 1 and it is greater than 0, at that time, amplitude decreases. That is, signal is attenuated. So, if this is x of n, then here you can see the difference in amplitude, that is y of n, because a is less than 1 and it is greater than 0. Next, when a is equal to 1, you can represent it as a or alpha. Okay, I'll call it as a. When a is equal to 1, signal remains unchanged. Okay, that is, if it is equal to 1, then both the input and the output signal amplitude will be same. Next, when a is less than 0, the signal is inverted, that is, it is flipped about the horizontal axis and it is scaled. So here this is x of n. When a is less than 0, the signal will be flipped. Now here this is the example. Here we'll take x of n is equal to sine of 0.2 pi n. When you plot this, or when you execute this instruction and you type the program and you execute, you will get this. That is, this is sinusoidal signal. Okay, so here this is x of n, input signal. Now we'll scale this input signal with a scaling factor a is equal to 2. So the scaled signal is y of n is equal to 2 times, that is 2 times sine of 0.2 pi n. So here the amplitude increases. Okay, so here what happens? The amplitude doubles, but the frequency of both the signals, that is the input and the output waveform or signals, remains the same. Now, why is signal scaling done? First is amplification. It increases weak signals before transmission or processing. Second is attenuation. It reduces the signal amplitude in order to prevent the distortion or overload. Next, it is used in audio processing, which will control the volume of the music and speech signal. It is also used in image processing, where it adjusts the image brightness and the contrast by scaling the pixel values. Next, it is used in communication systems in order to control the signal power during the transmission and the reception. It is also used in control systems, where it matches the signal levels between the different electronic devices. And last, it is used in biomedical signal processing, where it adjusts the ECG, EEG and other medical signals for analysis. Okay, so here when you do the scaling, there will be change in amplitude only. There is no change in frequency or shape, and it is used in many real world applications. So here what we are doing, we are taking the signals. Okay, first we'll set the time index, that is n is equal to -10 to +10. So total we'll be having 21 samples. we'll take a first signal sine. Okay, that is a sinusoidal signal. Actually, we should take only one signal, but I have taken two signals here and have scaled only x of n, x1 of n. Okay, I have taken two signals, x1 of n and x2 of n, but I have scaled only one signal, that is the x1 of n. So x1 of n is sine of 0.2 pi n, and the second signal is the cosine signal, which is x2 of n is equal to cos of 0.2 pi n. This is the sine and this is the cosine waveform. Now the scaling factor we are choosing is a is equal to 2, which is greater than 1. So here what happens? When a is greater than 1, the signal will amplify. That is, the amplitude will increase. So this is the scaling operation. This is x1 of n, which is given as input. Scaling factor is 2, and we get the output as y of n, which is the scaled version. That is 2 times x1 of n. Now this is the graphical representation you get. This is for the first signal x1 of n. This is for the second signal. This is the sine signal. This is sine waveform. This is the cosine waveform. And this is the amplified. That is the scaled version of the first signal, that is x1 of n. So here the amplitude is doubled from plus or minus 1 to plus or minus 2. Okay, you can see here amplitude is plus 1 and minus 1, whereas in the scaled version it is plus 2 and minus 2. Now what happens in scaling is you will multiply a signal by a constant where it changes its amplitude, and the shape, that is the frequency and the phase of the signal, it remains the same. If a is greater than 1, amplitude increases. If a is less than 1 and greater than 0, amplitude decreases. If a is less than 0, the amplitude will invert, that it will flip around the x-axis, that is about 0. So this is the MATLAB program which we'll be using here. So here this is a MATLAB code. These all three are the basic commands which we'll be using in all the programs, that is CLC, clear on and close all. Then we will set the time index, and here we are taking the scaling factor. This is the first signal, this is the second signal, and here this is the scaled version, that is a into x1. Next we have to plot the first signal, second signal and the third signal. So here signal scaling, it changes only the amplitude of the signal, not its frequency or shape. This you have to remember. And these are the applications it is used in communication system, image processing, audio processing and the signal processing. So this is the program. We'll see the program step by step here. First is the CLC, which will clear the command window. Then clear all, which will remove all the variables from the workspace. And close all, it will open, it will close all the figure windows which are open. And these commands ensure that the program starts with the clean MATLAB environment. So always you have to start your MATLAB with these MATLAB programs with these three basic commands. Next is we have to define the time index, where we are writing it as n is equal to minus 10 to plus 10. It will create a discrete time index ranging from minus 10 to plus 10, and the signal contains 21 samples, and this vector represents the time axis for the discrete time signals. Then we have to define the scaling factor, that is a is equal to 2 we are taking, which means that every sample of the signal will be multiplied by 2. Now because a is greater than 1, the amplitude of the signal will increase. Next, we have to generate the first signal, where we are using it, the equation as x1 is equal to sine of 0.2 pi into n. Then this will compute the sine value for every sample of n. Next, we have to generate the second signal, that is the x2 is equal to cos of 0.2 pi into n, which is the discrete time cosine signal. Okay. Then we have to perform the scaling operation. So for scaling, we are using a variable y scale. Okay, you can choose any variable. I am choosing y scale is equal to a into x1. So it will multiply every sample of x1 of n by the scaling factor alpha. So here the output signal will be having the twice the amplitude, because we are taking a is equal to 2. The frequency, phase and the shape of the waveform, it will remain same. Next, we have to create the first signal subplot, that is first subplot. So for that, what you have to do is we have to take subplot 3, 1, 1, where it divides the figure into 3 rows and 1 column. And here we'll select the first subplot to display the original signal. So this is for displaying the original signal. So this here we are using stem of n, x1, filled. Okay, so this stem it will plot the discrete time signal. Then we are using the filled here. It will fill the markers for the better visibility. That is, you will get small round circles now at the top of each of the signal. That is because of this filled. Next, we have the title A. So here, this is the title. We are giving the title as A first signal x1 of n. So this will be the title for the first signal. Then we have to label the x-axis, we have to label the y-axis. Then we are adding the grid on, that is, which will add the grid lines for easier interpretation. Next, similarly, we have to go for creating the second subplot. So it will select the second subplot for plotting the cosine signal. Then here we'll go for plotting the third subplot, where it will display the scaled version. Subplot 3 comma 1 comma 3, that is 3 rows, first column, and third subplot. Okay, so here again same, we are using subplot 3 comma 1 comma 3 stem. Then title of this third is C signal scaling. We are using alpha is equal to or A is equal to 2 as a scaling factor. X label is n. Y label is what? Y label is the amplitude of the y axis for the scaled version. That is, it is double because we are multiplying it by 2. The first signal is multiplied by 2. Then grid on for better visualization. So this is the output when you execute the program. This is x1 of n, this is x2 of n, and this is the scaled version of x1 of n. Actually, you should not take x2 of n. It is okay if you show, if you use only the, that is x1 of n and x2, 2 times x1 of n. Okay. And here, this is the summary of the program. What it will do here, it will clear the MATLAB workspace and closes the previous figures. Then it will define the time index. It will set a scaling factor alpha is equal to 2 or A is equal to 2. Then we'll generate the sine signal x1 of n. Next, we'll generate the cosine signal x2 of n. After that, we'll plot the original signal. We'll plot the cosine signal for comparison. And then we'll plot the scaled version. Okay. So here what happens? The amplitude of the signal increases from plus or minus 1 to plus or minus 2. And the frequency and the phase, it will remain same. And also the shape remains same. There is no change in the frequency, phase, or the shape. So the signal scaling changes only the strength, that is the magnitude of the signal. And these are the applications which we have already seen. Okay. Now here we'll execute the program. So I'll copy the program from here. Take a new script. Okay. Now we'll execute this. I'll save this as scaling. Save. Now see, this is the output. Okay, this is the first signal, this is the second signal, this is the scaled version of the first signal. I'll make some changes in the program. So here I'll make it as 2 rows. I will remove this second signal, and this is 2, this is 2. I'm taking 2 rows, 2 columns. Okay, so second signal, I don't want to take it. I will add a percentage sign which will make this as a comment. Now we'll see and we'll execute. See, here what we are doing, we are getting only the first signal, and we are getting the scaled version of the first signal. So you can see here the amplitude of the first signal is +1 or -1, whereas the amplitude of the scaled version of this first signal is 2 times the x1 of n, that is, it is +2 and -2. Okay, so it's okay if you take the sine signal or the cosine signal. You can practice by taking any one of the signal, or you can take both also. So this brings us to the end of our demonstration on signal scaling using MATLAB. And we have seen how multiplying a signal by a scaling factor, it changes, okay, it changes its amplitude, then while it preserves its overall waveform characteristics. And a factor which is greater than 1 increases the amplitude, while a factor between 0 and 1, it reduces it. And the MATLAB makes this operation simple and allow us to visualize the original and scaled signals clearly through plots. And understanding the basic signal operations like scaling, it is essential for learning the digital signal processing. So I hope this demonstration made the concept easy to understand. So keep practicing MATLAB, exploring DSP concepts, and learning through experiments. Thank you for watching. Have a nice day. Bye-bye.